6 powerful functions of integrated circuits, ICs. Integrated circuits, ICs, are essential components in modern electronics, providing a compact and efficient way to combine multiple electronic functions on a single semiconductor chip. Here are 6 powerful functions of integrated circuits. Logic functions within integrated circuits are fundamental operations that manipulate binary data, zeros and ones, based on Boolean algebra. These functions are the building blocks of digital circuits and play a crucial role in processing information. Here are some key logic functions performed by integrated circuits. NOT gate, inverter. Symbol. Operation, outputs the opposite value of its input. If the input is 0, the output is 1, and vice versa. AND gate. Symbol. Operation, outputs 1 only if all of its inputs are 1. Otherwise, the output is 0. OR gate. Symbol. Operation, outputs 1 if at least one of its inputs is 1. If all inputs are 0, the output is 0. NAND gate. Symbol. Operation, outputs 0 only if all of its inputs are 1. Otherwise, the output is 1. NOR gate. Symbol. Operation, outputs 0 if at least one of its inputs is 1. If all inputs are 0, the output is 1. XOR gate, exclusive OR. Symbol. Operation, outputs 1 if the number of ones in its inputs is odd. Otherwise, the output is 0. XNOR gate, exclusive NOR. Symbol. Operation, outputs 1 if the number of ones in its inputs is even. Otherwise, the output is 0. These logic gates can be combined and connected in various ways to create more complex digital circuits that perform specific functions, such as arithmetic operations, memory storage, and data processing in microprocessors. Integrated circuits, especially those in the form of digital logic ICs, are crucial for implementing these logic functions in a compact and efficient manner. Microprocessors and microcontrollers are both integrated circuits that play central roles in electronic systems, but they serve different purposes and are designed for different applications. Microprocessor. Function. A microprocessor is the central processing unit, CPU, of a computer or a general-purpose processing device. It is designed to execute a wide range of instructions and perform general-purpose computing tasks. Microprocessors are commonly used in desktop computers, laptops, servers, and other devices where general computing power is required. Features. High processing power and capability to handle complex computations. Typically consists of an arithmetic logic unit, ALU, control unit, and registers. Requires external components, such as memory, input-output interfaces, for a complete computing system. Applications. Used in personal computers, workstations, and high-performance computing systems. Suitable for applications where versatility and computational power are critical. Examples. Intel Core Series, AMD Ryzen Series. Microcontroller. Function. A microcontroller is a compact integrated circuit designed for specific control-oriented tasks. It contains a CPU, memory, both RAM and ROM, input-output peripherals, and sometimes additional features like timers and communication interfaces. Microcontrollers are often used in embedded systems for dedicated control applications. Features. Optimized for specific applications and tasks, such as control, monitoring, and automation. Typically includes on-chip peripherals like timers, counters, communication ports, and analog-to-digital converters. Designed for low-power operation and often include sleep modes to conserve energy. Applications. Widely used in embedded systems, including home appliances, automotive control systems, medical devices, and industrial automation. Ideal for applications that require real-time control and specific functionality. Examples. Atmel AVR Series, Microchip PIC Series. Key differences. Versatility. Microprocessors are versatile and can handle a wide range of general-purpose tasks. Microcontrollers are specialized for specific applications and tasks. Components. Microprocessors typically require external components, such as memory and peripherals, to function as a complete system. Microcontrollers integrate CPU, memory, and peripherals on a single chip. Applications. Microprocessors are used in systems where computational power and versatility are crucial. Microcontrollers are used in embedded systems that require specific control and real-time operation. In summary, while both microprocessors and microcontrollers are essential components of modern electronics, they are designed for different purposes and find applications in distinct domains based on their features and capabilities. Memory storage in the context of integrated circuits refers to the ability of these circuits to store and retrieve data. There are various types of memory storage technologies used in integrated circuits, each with its own characteristics and applications. Here are some key aspects of memory storage in integrated circuits. 1. Random access memory, RAM. Volatile memory. RAM is volatile memory, meaning it loses its contents when the power is turned off. Fast access. Provides fast access to data and is used for temporary storage during program execution. Types. Dynamic RAM, DRAM requires refreshing to maintain data integrity. Static RAM, SRAM does not require refreshing, faster but more expensive. 2. Read-only memory, ROM. Non-volatile memory. ROM is non-volatile, retaining its data even when the power is turned off. Permanent storage. Typically used for storing firmware, BIOS, or other essential system instructions. Types. Mask ROM, data is permanently encoded during manufacturing. Programmable ROM, PROM can be programmed once. Erasable programmable ROM, EPROM can be reprogrammed and erased using ultraviolet light. Electrically erasable programmable ROM, EPROM can be electrically erased and reprogrammed. 3. Flash memory. Non-volatile and rewritable. Flash memory is non-volatile and can be rewritten, making it suitable for data storage. Used in storage devices. Commonly used in USB drives, memory cards, and solid-state drives, SSDs. NAND and NOR flash. NAND and NOR are two main types of flash memory, each with its characteristics and use cases. 4. Cache memory. High-speed storage. Cache memory is a small-sized type of volatile computer memory that provides high-speed data access to a processor and stores frequently used computer programs, applications, and data. L1, L2, and L3 cache. Modern processors often have multiple levels of cache, L1, L2, and sometimes L3, to optimize data access. 5. Registers. Fastest storage. Registers are small, high-speed storage locations directly accessible by the CPU. Instructions and data are temporarily stored in registers during program execution. 6. Memory hierarchy. Levels of storage. The concept of memory hierarchy involves organizing different types of memory based on their speed, size, and cost. Faster and smaller memory types, e.g., registers, cache, are closer to the CPU, while larger and slower types, e.g., RAM, storage devices, are farther away. Integrated circuits leverage these memory storage technologies to provide efficient data handling and storage solutions for a wide range of applications, from temporary storage during computation to long-term data storage in electronic devices. Analog signal processing involves the manipulation and modification of continuous analog signals. Integrated circuits, ICs, designed for analog signal processing play a crucial role in various applications where signals are continuous and vary smoothly. Here are some key aspects of analog signal processing and the functions performed by related integrated circuits. 1. Amplification. Function. Amplifiers are used to increase the magnitude of analog signals. They can be designed for different purposes, such as audio amplifiers for speakers or instrumentation amplifiers for precise measurements. IC type. Operational amplifiers, op-amps, are commonly used for amplification tasks. 2. Filtering. Function. Filters are employed to modify the frequency content of a signal by allowing certain frequencies to pass while attenuating others. Low-pass, high-pass, band-pass, and band-stop filters are common types. IC type. Active filters, often implemented using op-amps, are widely used in analog signal processing. 3. Modulation and demodulation. Function. Modulation involves varying the properties of a carrier signal with the information signal for transmission. Demodulation is the process of extracting the original information signal from a modulated carrier. IC type. Integrated circuits designed for modulators and demodulators are used in communication systems. 4. Signal conditioning. Function. Signal conditioning involves preparing a signal for further processing or measurement. This may include amplification, filtering, and other adjustments to improve the quality of the signal. IC type. Instrumentation amplifiers and signal conditioning ICs are used for precision signal processing and measurement applications. 5. Voltage regulation. Function. Voltage regulators maintain a stable output voltage regardless of variations in the input voltage or load conditions. IC type. Linear voltage regulators, such as those based on op-amps, are commonly used for voltage regulation. 6. Analog to digital conversion, ADC, and digital to analog conversion, DAC. Function. ADCs convert analog signals into digital form for processing by digital systems. DACs convert digital signals back into analog form for output or further analog processing. IC type. ADCs and DACs are essential components for interfacing between analog and digital systems. 7. Voltage to frequency conversion. Function. Converts an analog voltage signal into a frequency signal. Useful in applications like frequency modulation and analog to digital conversion. IC type. Voltage to frequency converters are available as integrated circuits. 8. Phase-locked loops, PLL. Function. PLLs are used for frequency synthesis, clock recovery, and demodulation. They lock the phase of one signal to the phase of another signal. IC type. PLL ICs are widely used for frequency control and synchronization. Analog signal processing ICs are critical in applications such as audio processing, communication systems, medical devices, and sensor interfaces. They enable the manipulation and conditioning of continuous signals, allowing for precise control and adaptation in various electronic systems. Power management in the context of integrated circuits involves the control and optimization of electrical power within electronic devices. Integrated circuits designed for power management play a crucial role in improving energy efficiency, extending battery life, and ensuring the reliable operation of electronic systems. Here are some key aspects of power management and the functions performed by related integrated circuits. 1. Voltage regulation. Function. Voltage regulators maintain a stable output voltage despite variations in the input voltage or load conditions. They ensure that electronic components receive a consistent and appropriate voltage. IC type. Linear voltage regulators and switching voltage regulators are common types used for voltage regulation. 2. Power supply sequencing. Function. Ensures that different power supplies within a system are powered up or down in a specific sequence. Prevents issues related to improper initialization and voltage levels during system startup. IC type. Power management ICs often include features for power supply sequencing. 3. Power on reset, POR, and brownout detection. Function. Power on reset circuits ensure that a microcontroller or system is properly initialized when power is applied. Brownout detection circuits monitor the power supply voltage to prevent malfunctions during low voltage conditions. IC type. Dedicated POR and brownout detection ICs are features integrated into microcontrollers. 4. Battery charging and management. Function. Manages the charging of rechargeable batteries to optimize charging speed and prevent overcharging. Monitors battery status and reports information such as capacity and health. IC type. Battery management ICs and charge controller ICs are used for efficient battery charging. 5. Energy harvesting. Function. Captures and stores energy from ambient sources, such as solar or vibration energy. Used in low-power and remote devices where traditional power sources may be impractical. IC type. Energy harvesting ICs and power management ICs designed for ultra-low power applications. 6. Dynamic voltage scaling, DVS, and frequency scaling, DFS. Function: adjusts the operating voltage and frequency of a processor based on the workload. Reduces power consumption during periods of low activity. IC type: power management units integrated into processors or dedicated ICs for dynamic voltage and frequency scaling. 7. Sleep modes and power gating. Function: puts certain components or the entire system into low power modes during periods of inactivity. Power gating involves completely shutting off power to specific sections of the device. IC type: power management ICs and features integrated into microcontrollers and processors. 8. Thermal management. Function: monitors and manages the temperature of electronic components to prevent overheating. Adjusts performance or activates cooling mechanisms as needed. IC type: thermal management ICs and features integrated into processors and systems. Power management integrated circuits contribute significantly to the overall efficiency and reliability of electronic devices by optimizing power consumption, extending battery life, and ensuring stable operation under varying conditions. These ICs are crucial for meeting energy efficiency standards and improving the sustainability of electronic systems. Communication interfaces in integrated circuits facilitate the exchange of data between different components or devices within an electronic system. These interfaces define the protocols and standards for transmitting and receiving data, enabling seamless communication between various parts of a system. Here are some key aspects of communication interfaces and the functions performed by related integrated circuits. 1. Universal Asynchronous Receiver Transmitter, UART. Function: UART is a serial communication protocol for asynchronous data transfer between devices. Used for point-to-point communication between a microcontroller and other devices. IC type: UART modules integrated into microcontrollers or standalone UART ICs. 2. Serial Peripheral Interface, SPI. Function: SPI is a synchronous serial communication protocol for full duplex communication between a master and multiple peripheral devices. Commonly used for communication between microcontrollers, sensors, and other peripherals. IC type: SPI interfaces are often integrated into microcontrollers, and standalone SPI controller ICs are also available. 3. Inter-integrated circuit, I2C. Function: I2C is a multi-master, multi-slave synchronous serial communication protocol for connecting various digital devices. Used for communication between components like sensors, EEPROMs, and other peripherals. IC type: I2C interfaces are integrated into microcontrollers, and standalone I2C interface ICs are available. 4. Universal Serial Bus, USB. Function: USB is a standard interface for connecting and powering devices, supporting high-speed data transfer. Used for a wide range of applications, including connecting peripherals to computers and powering mobile devices. IC type: USB controllers are integrated into many devices, and standalone USB interface ICs are available. 5. Controller Area Network, CAN. Function: CAN is a robust serial communication protocol used in automotive and industrial applications for real-time data exchange between devices. Enables communication between electronic control units, ECUs, in vehicles and industrial automation systems. IC type: CAN controllers are integrated into microcontrollers, and standalone CAN controller ICs are available. 6. Ethernet. Function: Ethernet is a standard for wired local area network, LAN, communication. Used for high-speed data transfer between computers, routers, and other network devices. IC type: Ethernet controllers are integrated into network devices, and standalone Ethernet controller ICs are available. 7. Bluetooth and wireless communication. Function: Bluetooth and various wireless communication protocols enable short-range wireless data transfer between devices. Used in applications like wireless headphones, IoT devices, and communication between mobile devices. IC type: Bluetooth and wireless communication modules are available as standalone ICs. 8. Radio frequency identification, RFID. Function. RFID enables wireless communication for identifying and tracking objects using radio frequency signals. Used in applications such as access control, inventory management, and contactless payment systems. IC type. RFID reader ICs and RFID transponder ICs facilitate communication in RFID systems. These communication interfaces are critical for the interoperability of diverse electronic components and systems. Integrated circuits designed for communication interfaces enable efficient and standardized data exchange, contributing to the seamless operation of modern electronic devices and networks. These functions highlight the versatility of integrated circuits in enabling the functionality of a wide range of electronic devices, from simple gadgets to sophisticated computing systems. The miniaturization and integration of multiple functions onto a single chip contribute to the efficiency, performance, and compactness of modern electronics.